Yeah. So the goal today really is maybe 50% of the time, Mahmoud is downloading his brain onto us. The other 50% of the time are questions. So I want everybody in this room to be thinking of questions about how maybe their work could be influenced by graph models, how the tools work that Mahmoud is showing. You know, there's no stupid questions. It's all fair game. Everybody in this whole room should have at least one question that they ask today. Hopefully more than one question. So about 50, I would say it's about 50-50. We have 2 hours scheduled for this, so should have plenty of time. But please think of questions to ask related to graph modeling and Mahmoud's experience and knowledge and know-how. Those of you that are far away from the mic, when you do ask a question, we might have you come over and sit in one of these chairs real quick to ask the question so people online can hear us. Oh, does that work? Can you guys talk into it?
Yeah, it looks like it works.
Yeah, we can hear you.
You guys can hear Philip? Oh, wow. Okay.
Loud and clear.
Never mind. All right. We got complete. I didn't realize there was that good of a hybrid system here. Perfect. Okay. So those of you online, same thing. It would be great. Probably not quite as crucial, but it would be great if you all had questions. Ideally, we'd have more questions than what we can handle today. And those questions could also be asked on Slack. And Mahmoud can answer those questions later after today's session. All right. Mahmoud, I'll let you take it away.
Okay, yeah, thank you. Thanks, Blake. Okay, anyway. Okay, thank you everyone for attending this workshop. I have just one announcement before I proceed to this workshop. It was supposed to be a 2-hour workshop, but to be honest, I thought that it might be better if I give an overview first. Today, it will be a big picture about the graphs. Then maybe in the future, I'll divide it into different YouTube videos or something about more details about the tools and techniques and different libraries that are used for graph modeling and the graph neural networks. Okay, so today you can expect that I'll give the big picture about graphs, and then I'll give a very short hands-on about the tools that can be used, but not in too detail. So first of all, what are graphs? Graphs are, very simply, they are made of nodes.
I don't think they can send anything.
Oh, sorry.
Yeah, okay.
Can you see now?
Yeah, can see now.
How about this?
Yep, can see. Yes.
Oh, okay, that's great. So what are graphs? Graphs are data structure which is simply made up of nodes and links. Anything that could be represented as relations between two objects can be represented in the form of graph. Let's think about anything in any data source in the world that can be represented in the form of nodes and relations. We can represent them in the form of graph. For example, the nodes could be two people who are talking to each other, and the message that are transferring between two people is the link between this graph. Could be also two mobile phones that are connected to each other by one or others. This graph also could be the social network, such as LinkedIn. So any two people who are connected on LinkedIn, the person can be a node, and the relationship between them could be the link. The same can be applied to so many applications. For example, the friendship on social media, the following users on Twitter or on Instagram and so on. The WhatsApp messaging. Also, it could be two buildings and the streets that connects these two buildings. This could be the link between these two buildings, or maybe a corridor in the building that connects different rooms. So this could be also another example of graphs. Or it could be the door that links between two spaces, and so on. So the idea here is that it would be good if anyone can think about how can he convert his problem that he is working on right now, how can he convert the data into graph representation? And then we can discuss by the end of this workshop. So if you have any data that, I mean, if anyone have in mind some idea about the problem that he is working on, how can we convert this in the form of graph representation? Okay, so there are several types of graphs, and there are several divisions of how these graphs are constructed. The first one is called undirected graphs. And undirected graphs, this means that the direction of the link is not important. For example, in Facebook, the friendship, once you add the friend in Facebook, both of you will become the same friends, right? However, there is directed graphs like the relation in Twitter. If you follow someone, then you follow him, but this is not necessarily that means that he follows you. So there is a direction in the link in this case. The same as, for example, for WhatsApp messaging, you send message to someone, but this doesn't mean that he sends to you. Okay, so the direction in this case matters. Also, there are two types based on the links. So there are something called weighted graphs and unweighted graphs. The weighted graphs are the types of graphs where the links between two objects have some weight. So for example, if we looked at the Google Maps or any types of maps, whenever you link between two destinations, there is a distance, or there is a distance between two buildings or between two destinations. So this distance is the weight of the link between these two objects. Okay. So this could the weight could be the distance, the Euclidean distance. It could be the time that's spent between two places, and so on. There are so many applications to this. The other type is unweighted graph, which is the very simple graph that just nodes are connected to each other without any additional information to the links. Also, we can divide them based on their simplicity. So there are two types. The first one is simple graphs, or they are also called homogeneous graphs. And there are attributed graphs, which are called heterogeneous graphs. For the simple, there is no additional information between the links or the nodes. However, if we look at the attributed graphs, these are more representative of the real world, because they can express, or they can represent the complexity of the real world. For example, if we look at each node can have so many attributes, and also each link between two nodes can have so many attributes. Okay, so these attributes could be just a number, or it could be a variable. Also, we can add more complex information or attributes, such as images. So the attributes could be an image, it could be sound, it could be a video, it could be also something like text, and so on. Furthermore, we can add attributes to the links or the nodes in the form of functions. So attributes could be a function that does something. And this is what makes the attributed graphs very rich to represent real-world problems. There are other types of graphs, such as bipartite graphs and tripartite graphs, and also signed networks and so on. So different types of graphs. Okay, so now any data could be represented in the form of graph. So for example, this is the normal network that is used normally. However, if we look to other types of graphs, for example, the trees are very special types of graphs, where there is a root. The main parent of the tree is called the root node, and also there is a direction between data that flows in only one direction. Okay? And each parent have one or more children. Okay. Also images. Images are constructed in the way that could be represented in the form of graph, because they are constructed in the form of pixels, and each pixel has adjacent pixels from all the sides. So we can also represent them in the form of graph. And also we can apply different machine learning that are applied in images. The text also, on the other hand, the text can be represented as a graph, because the text basically is a sequential types of data, right? So we can represent them in the form of graph. If we look at the text, each word as an object, and the subsequent word also is another object, and they are linked by links. Now we know how can graphs be formed. Then how can we represent the graphs in the form of mathematically? We represent them in two main methods. The first one is called the adjacency list, and the second method is called the adjacency matrix. For the first one, for example, if we have this simple graph here, it consists of different nodes, and then each node can consist of a list of different nodes that are linked to it. For example, A is connected to C, D, and B, so we can represent them in this form. Or we can represent them into adjacency matrix. And this matrix, for example, here in this example, it will have the number of columns which equal to the number of nodes in the graph, and a number of rows also that are equal to the number of the columns in the graph. And then whenever any node that are connected with other nodes here, it will have 1 as an input. Otherwise, it will be 0. For the undirected graphs, we can find that this matrix is symmetric. Means that if we took line like this, all the nodes here will be similar to the nodes here. However, if we looked at the directed or unweighted graphs, the matrix in this case will, instead of having ones and zeros, it will have the weight of each link between two nodes. Okay, and this actually, being able to present the graph into the form of matrix, this makes it machine learning friendly. So we can use this as an input to different machine learning applications. So this is the starting point that we can use to convert the graph into different machine learning applications. Now I move to talk about.
Can I ask a question?
Yeah, sure.
Is there a way to represent the direction in the agency matrix? Because there's the weight, but the direction is not included.
Yeah, this is a good question. So yes, for the direction here, we start with the rows first. If the node B is connected to the node A, so we have we have 2 as the weight of B is directed towards A, but A is not directed to A.
Right.
So we don't have any value here. Okay. So this what makes the undirected is symmetric, but this one is not symmetric.
Exactly.
Okay. Now we move to talk about the graph data analysis, and this is, if we looked at this huge graph, this types of graph doesn't give any information. It doesn't give any new information, and it's referred to as the hairball graph. So we need to use the graph data analytics to extract useful information from graphs. And there are so many examples of data analytics algorithms that can be applied to graphs. This is not an exhaustive list. It's just a sample of these algorithms. But there are tons of algorithms actually that we can look for. For example, there is something called community detection. If we have a large graph and we need to detect what are the communities out there, and I mean by the word community here is that what are the subgraphs of the main graph that are very linked to each other. So any node in this subgraph is linked to each other. This is called the community. And then also we can use something called clustering of the graph. And the clustering is different from the community in that we can cluster these nodes based on some attributes. For example, if two people in the same in the social network have the same hobby or something like this. So we can just cluster them based on one or more attributes. Also, we can use graphs to detect anomalies, and also for other applications such as pattern matching, if we need to match some pattern based on the structure. Yeah, so there's another thing. We can use all these data analysis either on the structure of the graph or on the data that each node has. So we can the pattern matching, for example, we can extract patterns that have the same structure. So each node are connected. Let's say we have the same types of tree architecture or something like this, or based on the attributes that each node has. Then there are also some very interesting applications, such as the shortest path. This is also one of the main data analysis that are used on graphs, and this is used widely in the building related things.
Yeah, each time you use Google Maps, you're basically using this.
Yeah, exactly. So yeah, so it's an optimization problem. So for example, if every time you use Google Maps, basically they solve this issue, the shortest path, and also it's used for indoor localization and path finding and all these things. And also it's applied widely in different applications. This is an example. This is one example that I found that is using the shortest path to allocate or to reshape the layout of the interior design of building, and also to find out where are locations in the building that have high density or that can constitute a bottleneck for in the COVID-19 and these things.
Sorry, can you admit Charlene? I think she's.
Oh, sorry.
Well, this looks very useful to salt mine, right?
Yeah,
that's interesting.
Is she? She's joined the video.
Oh, if she didn't get in, then maybe you could, if she pops in again.
Okay, yeah. Yeah, so the main issue, I mean, the main problem that the main skill that we need to have so that we can solve our problems is to find a way to construct the graph and use different data analysis to extract useful information and then to process this information as well. So this is the task the main task that we need to think about whenever we need to solve a graph problem. There is also another interesting algorithm that's used. It's called small world, and this is inspired by the word. The world is small. So in this algorithm, this algorithm states that whenever you would like to connect to anyone, you have only 6 degrees of separation between any person. For example, if I'd like to meet Elon Musk in person, then in average, I need to meet at least 6 people before I can meet Elon Musk. This could be more, it could be from 2 up to 10, but this is based on experiment that's been done. The small world algorithm, it says that how many people or how many nodes you need to meet, you need to visit before you find the destination node. And the shortest, the better. So, for example, now there are 5 degrees of separation. If you can reduce them to 1 or 2, that would be much more efficient. Also, one of the algorithms out there is the node degree, and the centrality analysis of the node. For example, the node degree means that how many other nodes are connected to the source node, and the centrality means how important is this node to the whole graph. For example, if we look at this graph here, the red node here is very central. Means that if I remove this node, then we have separated the graph into 2 different graphs. However, if we look, for example, to this green node here, if we remove this green node, then none of the graph will be affected. And also there are other types, there are other analysis such as connectivity analysis and other types of analysis. I like to refer to the documentation of one of the libraries that are used for graphs. It's called NetworkX, and there are tons of different algorithms that can be used. So yeah, so these are all algorithms, and then each algorithm has the mathematical annotation and what it does and its application.
That's not shown on
Are you showing?
Oh, sorry. Yeah, there we go. Yeah, so this is the Network X as one of the libraries that are used for graph analysis, and you can find so many applications, so many algorithms that are used for graph analysis and with different applications. Yeah, and also the mathematical annotation behind this, or the mathematical basis, and so on. Okay, now I move to talk about graph neural networks. And graph neural networks are the neural networks that operates basically on graphs. And the main objectives of the graph neural networks are node classification, if we need to classify the node or to know what's the category of different nodes, and also link prediction if we need to predict whether there is a link between two nodes or not, and also finally, last but not least, the attribute prediction, which we can predict with different attributes of the node and the link. There are different types of graph neural networks. One of them is the graph convolution neural networks. And the concept of the convolution neural network is inspired from images, from image recognition. And the convolution neural network basically based on, let's say there is, it operates on images basically. So for example, there is a window like this, which slides across the image. And at each point, this window can filter the part of the image, and then it reduces the size of the image based on the area that it visits. And it keeps sliding across the image until we reduce the size of the image into the next layer. And from the next layer also we slide another window until the next layer, and so on. And if we look to graphs, also graphs could be represented in the form of, the images could be represented in the form of graph. However, the reverse way is not possible, because graphs are not structured in the same way as the images, right? In this case, here comes the adjacency matrix to solve this issue. So we use the adjacency matrix with adding some filters and adding some more details, so that we can represent the graph in the form of convolution that can be represented, or that can be converted into a graph convolution neural network. The other type of graph neural network is called the graph embeddings. And in the graph embedding, we try to convert or to encode the original graph into a lower dimensional space, where the distance between each two nodes in the roll dimension, or in the lower dimensional space, will represent the similarity between the two nodes in the graph. Okay, so then this could be applied to any other prediction problems. The idea here is that we need to extract the encoding. How can we convert the input network into the lower dimension space? And here comes the embedding problem. Oh, sorry. Yeah, so sorry, I'll say it again because the pointer is not working. So yeah, so this is the source graph, and then we need to convert it into a lower dimension space like this. And the problem is that we need to extract the encoding, or we need to do the function, to define the function that encodes the graph into the lower dimensional space. And to use this, first we look at the source node, which is this one. Okay, and then we try to sample all the adjacency node from this one. And the problem that we try to solve is that we try to predict the class of the source node based on each context. Okay, and to do this, we go through if we think about this as the source node, and then we take the adjacency to this node, which are all the nodes that are linked to it, and from the adjacency node, we take all the second degree adjacency from these nodes. Okay, so and then we aggregate all the information from each node and put them into the source node. I simplify it again. So for example, this is the source node here. So we aggregate the 3 nodes in the surrounding of this node. We aggregate the information of this node. And then we also aggregate all the information from the surrounding or from the adjacency. We aggregate them into this source node here. And then all this will be converted into a neural network where we can run a prediction problem using the aggregations. For example, this is the source node A, which is here. Sorry, this is the source node A here, the target node. And then A is connected to B, C, and D, right? And then B also is connected to C and A. So we aggregate also the information from C and A into B and so on. And we go with this for all the nodes in the graph. However, this is computationally it's very expensive, because if we go through all the nodes in the graph and did this aggregation, it will be very expensive. For this reason, we do something called random nodes. So we pick any node and then we go randomly through the nodes that are in the adjacency, so that we reduce the complexity of the problem. Yeah, so yeah, and then we solve this. This could be solved as a neural network where we can predict the A based on the attributes of A based on its adjacency nodes. There are several other types of graph neural networks that exist. There are tons of them actually. So, and these are the graph neural network models, and these are the GitHub repository for each of them. This one, for example, GraphSig is one of the most famous ones of them, and it's also used for the embedding of graphs. But however, this type of graph embedding, we can add new data to the graph without needing to rerun the model again, because it uses also the same concept of aggregating the surrounding. Yeah, so this is also some of the graph neural networks that are used. Yeah, there are also some of the topics, if anyone would like to expand his knowledge about graph neural networks. So this GitHub repo also is very useful. Anyone can read about it. It consists all the papers and everything about graph neural networks. So yeah. For the software that are used, there are also a lot of software that can be used for either for graph database management or for graph data analysis. However, personally, I have used Neo4j for the graph database management system and NetworkX for graph neural networks. Now I'll show you a very quick introduction about Neo4j. Okay, so this is Neo4j, and this is the data from the SDE4 building. So, and this is the interface. This is the old interface about Neo4j, because this is Neo4j is the graph database management system. Means that we can query any data from the graph, and we can manage the data, and we can link to different nodes or different links. I mean, we can manage the whole database of graph. Okay, and also we can read, for example, if we need to read, let's say, IFC file and convert it into graph, then we can look at the schema which constitute the IFC. For example, there is something called the RDF, and the RDF is the schema behind the IFC. So we can just extract the whole RDF file and convert it into Neo4j, and from this any building we can extract different information from.
Mahmoud, so RDF is what? About format?
A schema, yeah, it's the schema that IFC is built on.
Okay.
So it consists of information about how different objects are linked to each other in the IFC file.
And RDF is something you just upload into Neo4j and it.
I haven't done this in my project,
Okay.
but yeah, usually it's used like this. So I know other people from different. People who have been working on converting Bim into graphs.
Okay.
They use the RDF as input. So first they import the RDF file into Neo4j, and the RDF file consists all the required information that are used to construct a Bim model for IFC. And then they import another file, which is the building information model for a specific building. And then they use the information that has been extracted from the RDF. They used it to extract different information from the IFC file. So yeah, there is.
So if you didn't use RDF, what did you use?
Okay, so in my case, I used the software called Qgis, and this is spatial. This is a spatial analysis tool software, and I built some plugins inside this.
Philip, this is what you use, right?
Yeah, that's what I teach in.
Exactly what he teaches. Okay, cool.
Yeah, actually, yeah.
Sorry, Philippa, you had your hands up too. You want to ask a question?
Yeah, no, I only wanted to ask if the scheme is only inside the IFC file, or if I can find, for example, within a Revit file.
So the IFC is built upon different schemes. One of them is the RDF, and there is also, I think there is also they have XML scheme that can be used, but the RDF is the one that can be extracted in Neo4j. So Neo4j has an interface to RDF.
So if I have a Revit model, my Revit program will export what file format?
IFC. So
Okay.
if you have a Revit model, first you have to export it into IFC, and then you import it into Neo4j as from IFC.
Okay, so I can directly, let's say, extract RDF from Revit. I need to have the intermediate pass on IFC format.
Yes, exactly. Yeah.
Thank you.
So Revit to an IFC file, IFC directly loads into Neo4j.
No, we have first to extract the RDF schema first to Neo4j, and then from Revit we export to IFC.
Revit, IFC, RDF, Neo4j.
Yes.
That is a way to do it, but that's not the way you did it, right?
Yeah,
You're gonna show us what you
I
did,
can
right?
see. I can share with you one of the papers that have been published on using this method.
Okay.
But in my case, I didn't need all this complexity for my research. So I used the Qgis, and I built some plugins for the Qgis that can automatically extract the relative information that I need. Because I didn't need to extract all the data from the Bim model.
So you went from Revit to QGIS.
Yes.
What's in between that?
So from Revit to QGIS, and then I did spatial discretization so that I divided the space into different nodes.
How did you go from Revit to QGIS?
So first I extracted Revit to CAD, and then from AutoCAD to QGIS.
To AutoCAD, so a DXF file.
Yes.
And then you open the DXF file in QGIS.
Yes. Yeah, exactly.
But you lose, DXF files do not have attributes related to the lines, right? You don't know it's a wall or a window.
Yes. So so when I extracted them from Revit to DXF, the information are stored in the layers themselves. So each
the
layer.
names of the layers are the attributes.
Yes, the name, and also they have some information inside the name. But I'll show you an example here.
Okay. Is anyone here lost? Does everyone know what Revit is? No? Okay. Revit is a building information, it's the most popular building information modeling software in the world. IFC is a supposedly open international standard for exchanging building information models. It doesn't work super well. No, not many people use it, I think. This is a very controversial thing for me to say. I'm just trying to be as open as possible. It's probably similar to the GIS community. You guys probably have information exchange formats that are not perfect, right?
Yeah, but also IFC is relevant for the geospatial community. A lot of research is going on to bridge architecture and geospatial, meaning IFC to some GIS format.
Okay, got it. Yeah.
Yes, I agree with you. It's a terrible format.
IFC?
Yeah, and it's not controversial. Everyone knows it.
Everyone knows it.
Yeah.
Why is it controversial? Because not many people actually use it, right?
Yes, and it's very complicated.
Very complicated, okay. But Mahmoud, you created a sort of alternate method. You used Revit to AutoCAD is the old version of Revit. It's just lines. It creates, it's the digital form of sketching things, basically.
Yeah, because actually to convert from Revit directly into Qgis, it's not possible. So you have to convert them first into AutoCAD or other different.
A DXF file, right? Or DWG file.
Yeah, if there is a way to convert them into GeoJSON, this is much better.
So your Revit file had these layer types, right?
Yes, but I have also to simplify them and remove many of the data that are not used. Because
So you manually did that?
yeah.
Okay.
But why didn't you use the first way that you showed on your slides with the RDF format?
So my application in this case is different from using directly the information from the Bim model. I needed to add another layer, which is the spatial discretization. So I need to add to divide the space into different nodes. And this doesn't exist in any Bim model.
But okay, so this is an intermediate step that you had to do because you wanted to discretize the spaces.
Yes.
Okay. The BIM model is the BIM model supplied by Adrian's team. They built it, I think, from scratch, correct?
Yes.
It's replicated from the construction, from the original design.
So the company who designed SD4 had a BIM model.
And we like duplicate from that because.
And you guys duplicated, okay. So just so everyone's on the same page, a building information model has all these attributes. This is a wall, this is a window, etc. AutoCAD does not, right?
Yes.
But AutoCAD has something called layers. So
Yes.
the BIM model you can extract from Revit into AutoCAD, and there's these layers came up, right?
Yes, exactly.
And then in AutoCAD, you removed layers that didn't help you.
Yes. And
Okay.
also there is another big problem also that to convert basically between BIM and GIS is the projection because the GIS they use the longitude and latitude projections.
Okay.
Whereas if you looked at BIM model and AutoCAD, they use the metric the metric projection. So the meters and centimeters and these things. So to convert between them or to exchange between them, you have to realign the model manually. I don't know if there is a way to do this automatically or not, but you have to do this manually at the moment.
I have a question. So in your case, the drawings that you exported and processed, they are kind of disconnected, right? Like the level 3 and level 4, they have still the relationship.
Yes.
There is.
They are not connected in the BIM model, or I mean, they are not connected here in the GIS model. But once you extract them to Neo4j, you can they can be connected.
In Neo4j.
Yes, because Neo4j is the place where you connect everything together again.
So to stay at the high level real quick, so in your process, QGIS to Neo4j, right? That there was a.
Yes.
How does that link occur?
So I defined the buffer zone around, I mean, the area of influence of each object. Let's say this is the wall, and then this is the area of influence. And then I extracted the nodes that falls within this area of influence. Each node that falls within this area of influence will be linked to this object, which is the wall in this case. So the wall here will be linked to all the cells or the nodes that are located in this area of influence. And these nodes are also linked to the adjacent nodes, okay? And also the adjacent node might be linked to other spatial objects like the columns or the furniture and so on. From this, I can construct the whole graph because they are all be connected within the same nodes or the same cells, cell center. So the cells are the main thing that links the whole building together. Okay? And from this, we can run the different graph neural network application on these cells.
How do you get it from this to Neo4j?
This is very easy. I've developed build to vec, which is
So this is where build to vec comes in. Okay.
I mean, I just developed another plugin called build to vec also for Qgis that can extract these each cell, and it links it with the spatial object, and then export it as a CSV file, a simple CSV file, and then I import it here as a CSV file.
Is that a special type of CSV file? Is it
No, it's just okay. Yeah. So as I mentioned here, we have different types. We have the different methods of defining the graph. So I import it as adjacency list. So these are the nodes, and it will be linked to all the other nodes that are there. So it will be, the first column will be the source, and the other column will be the target.
But it must be some format that Neo4j recognizes as a graph.
There are some well-known formats, but
Okay.
it also can read any CSV file, and then you can use this is a database management system, so you can use the different scripts to define,
to specify your input file and how it works.
Yeah, exactly. Yes.
So it's a little bit like loading a flat file into pandas.
Yes, exactly. Yeah.
You're specifying with the attributes of read CSV.
Yeah, correct. Yeah, that's correct.
What is a column? What's the okay.
Yes, and then we can use also the Neo4j to extract different information. For example, if I have cells that are linked to walls and the same cells are linked to doors, then I can extract that these doors can be linked to this wall, or this door can separate between two spaces, and so on.
Okay.
So also we can reconstruct the information only from using graphs.
So go back to Qgis real quick. So you created a Qgis plugin.
Yes.
Is that plugin, how can we use that plugin? Is it on GitHub? Is it?
It's not in GitHub. It's just it's hosted here. Yeah, I uploaded it.
It's also called build to vec.
Yes.
Okay. How does one use plugins in Qgis?
So yeah, this is a very.
I should take Philip's class.
You can.
Do you have to write them in R?
No, you can use Python.
Gross. Oh yeah, good. All right.
So you can use a script from template, for example, like something like this.
Okay.
And it has so Qgis is very powerful because it has an interface to all the functionality that exists in the Qgis software itself. Or I mean all the spatial data analysis you can use. Simply you can use Python to do stuff.
So a plugin is really it's just a big Python file.
Yes.
And that Python script is designating what objects in Qgis that you want to extract and the relationships between them, and it's creating this flat file, this special flat file that you're then loading into QJ or Neo4j,
Yes, yes.
and this is all created by you.
Yes, exactly.
Okay.
I mean, yeah, there is a lot of manual stuff here, but we can automate some of these things. But yeah, I mean, for the sake of time, I just did it manually. Some of this stuff I have done the manually. This is how the graph. This is how the QGIS plugin looks like. For example, you input here the layer that you would like to select, and I mean then you run the plugin, and then the result will be automatically saved.
Cool.
Yeah.
I mean, we've got QGIS users here, right? We have the master of QGIS. I'm sure Penguin also uses QGIS. Okay.
Yeah.
This stuff is making sense to you guys.
We're also developing a plugin, by the way.
To convert what? What's the plugin?
It's more like a spatial processing plugin, taking data on buildings as input and outputting morphological metrics.
Okay, cool. So if we had QGIS models of NUS campus, you guys have those?
No, we don't.
No? Okay.
QGIS, it's basically used for maps.
Right.
Yeah,
Okay, cool.
but using them for the buildings, for inside buildings, this is an unusual use for the QGIS.
Why did you use it then?
Because it has a very rich library of spatial analysis.
Cool.
And for example, the other software that I've been using, it's called Grasshopper.
Yeah.
It has also so many applications, and the community is very big. But the issue is that it's still not yet as matured as QGIS.
Rhino Grasshopper.
Yes.
Right. Okay. Yeah.
And then also, if we use the QGIS in the form in the urban context, it would be easier to different buildings and rich information. So yeah.
Cool.
And it's free and open source.
Yep.
Yeah, I mean, yeah. So this is the interface of Neo4j. Once you import any graph or you build any graph, you can find these are the nodes with their labels, and these are the relations that you have between each two nodes. For example, I need to extract all the nodes that spaces and doors. So these are the links between the spaces and the different doors in the building. Okay. Building and level. So I was only working on level 3. So this is the building, and it's connected only to level 3, and so on. Level and space. So this is the level 3 and connected to, and so on. And then
sorry, what are each of these panels? This is the function of the interface of Neo4j where you can see queries.
Yes. So this is when you open the Neo4j for the first time, this is the interface.
Okay.
And then you start a new project.
But what you were just showing us is what is that?
This is the file that I've been used for the previously. I've been working on.
Okay.
It's SD4, the data that I've extracted from QGIS into Neo4j.
Can you go back to the?
Sorry, I have a meeting.
Okay.
Thank you.
Thank you.
Now you had a bunch of queries, right? You were showing us, right? So can you explain what's happening in this interface right now, this GUI?
Yes. So this is the data. This is the database information that you have for the Neo4j, and it contains all the data about the graph that you are working on. The nodes with their labels, the relationship types, and the relationship between each two nodes. Okay, and the properties. So we can have property for each node and for each link as well.
Property is like a class?
It's attributes of each node. I'll show in a moment how.
Okay, cool. I was just asking, like here on the right, you have these panels. These cells. These are cells or panels or something. Like what?
Yeah, this is like the notebook.
It's like a notebook format, right?
Format, yes.
Okay, that makes sense.
And then these are the favorite. I mean, you can add different, or you can use different existing scripts
Okay.
over there.
Is this Node4j database available somewhere?
And the new 4J?
For SD4, that
No,
database?
not yet, no.
But if I create a Neo4j account, you could send me
Yes,
that flat file.
Yeah, exactly.
And you could also, so the scripts and the flat files for SD4 are in a repository somewhere,
Yes, yes.
right?
Yeah,
So if I have a Neo4j account, I could use your scripts, I could use your flat files, and I could recreate this database.
Yes.
So right now, this database is in your Neo4j account.
Yes, yeah, exactly.
Or you could even share, you could share this with us, I guess, right?
Yeah, yeah.
You have Neo4j, okay. Okay, cool.
Yes, and this is where you write the script. For example, if I need to create a node, so yeah, I mean, there's a specific way to write scripts or to create things. For example, first I define all the variables, and then I write where, for example, n.
What is this query language called?
It's called Cipher.
Sorry, Side Park? Cipher.
Cipher. Yeah.
And that is a specific query language for Neo4j.
Yes, yes.
Okay, cool. Oh, look at that.
So yeah, so for example, if you would like to query any data from a graph, then you start typing match, and then the label of the graph, which is existing. Sorry. So these are the labels. For example, the label of the node that you would like to query. And if there are specific property that you are looking for, then you write them in the form of dictionary like this. And this is how the link looks like, or the relationship looks like. So you open this bracket, and then you write the relationship type or the link type from here. And then the next also the other node that you would like to query, and then you return whatever you have written here. I mean, yeah, it requires a bit of exploration, but it's very easy to use. If someone it might take only 1 day or 2 days to know the language. So, yeah, sure.
When you define this kind of property, you could define also all the properties you have in the first file, for example, in Revit, correct?
Yes. If you imported it as a CSV file, you can just refer to these properties and add them when you import the file.
Okay. When you export through the DVG and then you link within Qgis, you lose a little bit of properties. I mean, you are carrying on also the geometrical information of the model, is it correct?
Yeah, correct.
But if you theoretically could bring with you also the ID, the name, the material of a certain wall, for instance, you could write it down on the graph. It is possible to add it.
Yeah, exactly. Yes, correct. So yes, I mean, whatever the information that you have from the BIM and you have successfully exported, then you can add them as labels or as attributes in the new 4J. Yeah. So yeah, I mean, also, for example, let's look at so these are the information that we can get from. I mean, these are the properties of this space. For example, it has UID, it has the embedding. So this is the embedding vector of this space. It has geometry. In this case, it's a polygon, multi-polygon, which is extracted from Qgis, and the HVAC type is natural ventilated, and the name is so on. And you can add as many properties as you would like.
Cool, man.
So somehow in this process, you had to create these relationships because they're not in Revit.
If they exist, you can just use a script to extract all of them, and
That's your plugin to QGIS that's creating all of this that then gets loaded into.
yes.
You know,
But I mean, this is the way that I've used. But I think I mean, if there might be a bigger team or something, it could be automated directly. Yeah, I mean, we can eliminate many of these steps, and just automatically from Revit we can extract directly to.
I get that, but so in your process from, okay, let's say Revit to IFC to RDF to QGIS to Neo4j, you at some point had to like hard code these relationships in, right? Because the Revit file doesn't have HVAC as natural ventilation. Like,
Yes.
where did you do that? QGIS, I guess, right? Or is it
Yes,
the
yeah, exactly.
QGIS plugin that you wrote is making these connections and adding these attributes?
In this particular, in this particular property, I automated this because some spaces has air conditioning and some are not linked to air conditioning. So I have done this. But yes, you are correct. In many cases, sometimes I add them manually.
So NV, where is NV added? Is NV, if I go to QGIS, and click on a space, is it going to have an attribute NV?
No. This is done inside the Neo4j using the query language. So first, I extracted all the cells that exist that are linked to the air conditioning outlet.
Okay.
And then the cells are linked to a specific space.
Okay. Yeah.
Then once there is a cell that has that in the space and they are linked to air conditioning, and then this space is air conditioned.
Is AC or NV?
Yeah.
So in Neo4j, that's where NV was added to this, or?
Yes. And also we can add other properties that gives each cell each cell unique. Because the more we add attributes, the more the machine learning will learn better.
Okay. In GitHub, you have the plugin.
I haven't it yet, but
you will? Okay, you will definitely. Okay, so if you could help us by creating a GitHub repository that has the Revit file, the IFC file, the RDF file, what's the file format of QGIS?
I think I'm sure. I think there's. I'll explain.
Whatever the file format of QGIS is. The QGIS plugin, an example of the output of the QGIS, right? Which is some .csv file that has all these relationships.
Yes.
And then Neo4j, a Neo4j file.
Okay. Yes.
So that a person knows how you got from point A to point. This is more like point H, right? There's like B, C, D, E, F, G, right?
Yeah, but there's still another step, which is from Neo4j to do the graph neural network applications.
Okay.
The build to vec and the build to vec, because the Neo4j it exports the graph itself, the graph representation.
So you're exporting the graph model from Neo4j
to network X.
To network X, where you're doing the graph neural network.
Yes.
So back into Python.
Yes.
Okay, so that whole value chain from A to M or whatever, and a diagram of how that works would be helpful for all of us. If somebody wants to dive into this, they know how you got from each step to each step, and a little bit of documentation about what happens at those steps and what manual things you had to do. Like in QGIS, I had to manually do this and this and this and this, that kind of thing.
Yes.
That would be very helpful. Okay,
Okay, yeah. So
sorry, keep going. Go back to Neo4j because that's really cool and you were showing us some interesting stuff.
uh,
But sorry, let me interrupt you one more time. In this interface, the node labels, relationship types, property keys, these are all characteristics of a Neo4j model.
yeah,
You're creating all of these automatically in your QGIS plugin.
yes.
And when you load them into Neo4j, there's a script that you use to do that.
Yes,
And they just pop up this way, right? And in this interface, this GUI, you're clicking on these things and it's auto-creating a query, right? Okay.
yes, exactly. Or you can just type in this script here.
Sure, but you were clicking on like, and at some point, I interrupted you about 15 minutes ago, and you had a bunch of really nice, like, you had panels, and they all had queries, and you were showing us. Can you go back to that? Where was that?
This one?
No, like you had,
You were able to click on SD4 and then on the level, and then there was another pane where
Oh, okay, yes. So,
there was all these panels, and you were showing us the door space relationship, and then.
okay, so these are the nodes. This panel here is the nodes, and these are the relationships. If I need to extract all the relationships between cell and space,
Okay,
then I click here. But it limits only with for 25.
25.
Yeah.
Did you create those relationship types, or that's just like every permutation of relationship type in the graph model?
So these are extracted from QGIS.
Okay.
And then here in Neo4j, I added the labels of each relationship.
And that's just a list of all possible relationships.
Yes.
Okay. And if you click on it, you get this, okay, you get this nice little visualization. Interesting.
So I saw that links that in the graph that has all kind of different attributes, right? Do you also incorporate those kind of values in your neural network as well?
Oh, yes, yes. So for example, yeah, so the link here, for example, the link between the fan and space, it can have some attributes. It can add some attributes. And these can be inputted, yes, it could be inputted to the graph neural network.
Yeah.
Yeah.
Okay, you guys keep rolling. I need to take a bathroom break. Does anyone else want to take a quick break?
yes.
Okay, let's take a 10-minute break and come back right where you left off.
Okay.
Okay, thanks. Drink too. Phil gave me a bunch of green tea and that's not good for me. So I gotta.
Can't see the just video. You can see us.
Oh,
Is it like
oh, I think this one.
要不然这个局，那个局，
没有。首先我们有个今年的进来的编辑，然后就他做 presentation，他现在还没有用，那样可能要用操作，就是 WinSpeed 和 Win
this because I think it's really good stuff. And I don't want to.
Yeah, I'll start recording.
You can turn the video. Yeah, there you go. Okay, cool. Since we took a bit of a pause, I mean, yeah, I've been asking lots of questions, but does anybody else want to take the opportunity to ask something that you didn't get a chance to ask so far?
Yes.
June, yes, take it away.
So in your PhD research, actually you mentioned about the temporal, right? So how did you put temperature elements in your graphic neural network? So for example, I want to use the building data genome data set into this neural network. So I got lots of metadata like meter type, building type. I can put that into node, right?
Yes.
And for the link between the node, I can put physical distance. But how about the time series, like the energy data? How do I put into the graphic neural network?
Okay, yeah, that's a good question. So I explain what I have done, and then I'll explain what should be done in your case. So in my case, I needed to convert all the continuous data into discrete types of data, so that because my problem, I was solving a classification problem, so I need all the data to be discrete, categorized basically, and so I did the clustering first of the thermal comfort data and also the personal data of people. I clustered them into 10 different clusters, and these clusters I inputted them into the machine learning model. To do something that's temporal and changing over time, I think the best thing to do this is use one of the spatial the temporal graph neural network models. I'll give you an example here that I've been showing.
Each one, are you on the Zoom session now? So you can see that everyone can see him changing the screens and stuff. It's not, yeah, okay. It's not just like one. It's not stuck on one.
At the
Okay.
beginning, there was some issue, but it took long.
Now it's like his desktop and not the, okay, got it. Cool.
So yeah, so this is one of the models that exists is called Spatial Temporal Attentive Recurrent Neural Networks.
I think it's
Are
not.
you sharing the screen? Are we starting the?
Yeah, start, share screen, yeah.
I can see.
Yeah, share screen.
Oh,
There we go.
sorry.
Yeah, there we go. Okay. Important, this is important, guys.
Yeah, so this is.
Thank you.
So for the temporal, if you need it to be temporal, then you have to create adjacency metrics at each time step. And each, of course, because it evolves over time. So the links can be connected at the moment, and after one minute, it will not be connected. So you have to create adjacency metrics at each time step. And also you have to create labels metrics. The labels of each node. So you have the nodes and the rows of each node, and the classes of each node as columns. Okay, and the classes also must be integers or some number, numeric data. Okay, and also you have feature metrics in which that at each time step you can indicate what are the nodes. And then you input all these three metrics into the model. The model is called the Spatial Temporal Attentive Recurrent Neural Network, this one. And by doing this, you can predict the value at each time step.
Is this model very computationally heavy, or is it actually like scary?
No, it's very good. Yeah, actually it has been validated for some big models out there, and it's computationally very efficient. Based on what I've read.
So what phase is this? This is after Neo4j export, and as you're using star at the same time as your network X. Is it based on network X, or like how?
Yes, yeah. So actually, the Neo4j can extract the data in the form of new network X.
Okay.
So you can just import it.
The network X file. Okay.
But The idea here is that because this is a temporal type of model,
Yeah.
then we need, and it would be more useful if it's in real time prediction. Because so in this case, we might need something that can read the data in real time and convert it into adjacency metrics also in real time. But this data it will be only the temporal data. I mean, the temperature, the feedback from users, and so on. But the building spatial data itself, it will be fixed. It will be static.
Yeah. Okay.
So yeah, I mean, it will be just changing one or more of the columns in the adjacency metrics. It will be the only ones that will be changing. Yeah. So for example, the last two columns or something will be changing, and the rest of the metrics will be fixed. Yeah.
I have another question. So I'm wondering how robust is this process of extracting relationships? Because so it's from the application of converting Bim model to energy model. So the current approach is, one problem is the robustness, that people always have to double check the results and fill those gaps and correct those errors. And if this relationship extraction, the spatial relationship extraction is robust, that it can be automatically correctly extracted every time, I'm thinking it could be a solution to that.
Yeah, I think this is a good point to explore. Yes.
In your case, when extracting,
my case during my application to this model, it gave me a very good result. The results that I got, they were.
Do you need to manually correct some bugs after extracting the graph? Like for example, from level 3 drawing.
Yes.
Are you able to extract all those like doors and walls relationship every time?
Yes. Yeah. Yeah. In this case, I have to run the scripts so that I can identify the relationships for each space again. Yeah.
But aren't you dependent on the person who specified the layers of whatever? So you have Revit to CAD. Revit has those. I don't know how you got the layers in CAD. Did you also have CAD files?
No, from the Revit.
From Revit. So in Revit, there are different classes specified: wall, window, door. So whoever built that Revit model did a pretty good job of being quite consistent, right? But I think maybe what you're trying to ask is if you have somebody who's just learning Revit, doesn't have a clue what they're doing, builds a crappy Revit file, throws it at you.
Yeah, I think it will require so many manual. Yeah.
You have to go through and fix the Revit file before it's useful to convert into. Is that that's kind of what you're asking, right?
So it still depends on the data source.
Yes.
The quality of that Revit file, right? That's the age-old problem with any schema translation.
Yeah.
Is it's dependent on how well the initial schema was followed, or whatever you're trying to convert from something to something else.
Yes, exactly.
That's the age-old problem.
Yeah, this is the problem. Yes.
Okay.
And also defining the most crucial features from the BIM model itself, because I might not need all the data from the building information model.
So that process of determining what's crucial for your application of thermal comfort prediction was a thoughtful process that you went through when you extracted.
Exactly.
Okay, so it's all okay. So there's a lot of Mahmoud kind of like decision making based on the context. Of course, that makes sense. Yeah, that makes sense.
And it's application dependent. So if I'm doing it for visual comfort, for example, it will be different. I choose maybe totally different.
Okay, got it. Okay. So you could imagine a field of like, that's kind of a field of I don't know if research is the right word, but like Philip's not here, but he was just mentioning there's a bunch of work being done in the translation between IFC and GIS, right? And James, your team, you guys have, and I know Adrian has looked at energy plus to them and backward and back and forth, right?
Yeah.
And the ability to do that in a robust way is a type of research.
Yes, yes, yeah.
Yeah.
Correct.
I think, right? Is that a correct statement? Is that?
That's what I'm talking about.
Sorry?
That's what I'm talking about.
Yeah.
That's the problem. So I'm thinking because in Mahmoud's case, it's able to extract just the important information instead of all those like dimensions.
Right.
So it's probably more robust. Yeah, another question is it possible to incorporate all the HVAC system layout? Because now you are just looking at the spatial relationships, right? How about the mechanical side? Is it possible?
Yes, yeah.
Like this AHU supplies to all these like 15 zones?
Yes, this will require to, I mean, do we need the spatial representation of these objects? I think just the relationships only in the that's important.
Yeah.
And I think, yeah, we can just directly use the data from the IFC file because they are structured in the form of graph, actually. So we can just extract them directly and put them as maybe as nodes or something in the spatial representation.
In that case, we are skipping the Qgis step, right? Like feeding the IFC into Neo4j to some kind of.
We can skip Qgis if the location of the exact location of the people in the space doesn't matter for the result. Yeah, but yes, yeah, we can just if it doesn't matter the spatial form or shape of the object, then we can just extract it as a graph directly, a schematic representation, and then input it into any graph neural network. So yeah, so the problem from the beginning is how to form the problem itself, how to form the graph.
Sorry. And how about using directly from the beginning Dynamo? Did you try something? Because Dynamo is quite similar to Grasshopper that you said before. And it has a direct link with the Revit API. So a lot of the information that you extracted after the IFC, the DVG exportation, the IFC exportation could be.
Oh yeah, this would be a great idea. I think yes. I think Dynamo, since it's very easy to communicate with Revit, then it's easier to select a specific object from Revit and extract it.
You have simply like buttons that relate to the Revit category, Revit types, Revit elements. So I use every day at work. It's immediately related to the categories of Revit. So you could, for example, use the walls like a geometric entity and selecting, filtering only the instances that you need.
Yeah.
Okay, maybe we need only the 4th level walls.
Oh, that's good. Yeah, that's a great.
Then we can extract geometrical information, and because I saw the information you bring with you, it's mostly related to the geometrical position.
Yes.
Is it correct?
Yeah, that's a great idea.
By doing this by Dynamo, you can also extract all the other metadata that are inside the instance.
So my question is, how can we project it into the longitude and latitude elevation? Is it possible?
Three main coordinate systems within Revit that are like internal origin. That is the one that you use when you link the DXF in AutoCAD, but we have also the survey point and the survey point. That is the one that has north, south, east, ovest, and related to this point, there is a location attribute that is managed that are the properties you are looking for.
Yeah, I think in this case, yes, it would be much easier. So, I mean, we can extract the spaces and all the spatial objects, and even we can do the discretization of space in Dynamo itself, and then we extract them directly to a Neo4j in this case.
Yes, you can skip all the intermediate step.
Yeah.
And it works very well if you are, it depends on the model itself, obviously, but you have a lot of features, a lot of possibility to filter elements directly in the model that, in my opinion, could be helpful for your.
Yeah, that's a good idea. I just, to be honest, I was just focusing on open source, the open source files and data. So yeah, I kind of excluded Dynamo from the beginning. So yeah, but yeah, this is a great tool to use.
What is Dynamo?
Oh, sorry. Dynamo is the visual programming platform that is within Revit. It's like Grasshopper for Rhino. Okay.
Is it an Autodesk product?
Yes, it came with Revit.
Okay.
So if you need like Grasshopper inside Revit, basically it's called Dynamo. Yes, you have this kind of, it's like
visual programming also.
Yes, and you have the possibility to use inside it directly Python if you want it, because it has a Python engine inside. And is what
isn't the software that you use for Modelica also called Dynamo?
That's Damola.
Dymola. Okay, sorry.
I don't know.
Yeah, I was like, I thought you were talking about Modelica, and I was like, get out of here. No, I'm just kidding, just joking, but not. Okay, I've heard of Dynamo. Okay, but now this makes more sense.
It could be a way to fasten the process and to bring with you all the data you need, because I write in CSV files, but I work all the information that we need, for example, for cost estimation, all the kind of information you have in the model, you can bring with you with this kind of.
Yes, I think it is worth the exploration. Because we can extract all the relations in just one click.
Yes.
So,
Good questions, everybody. More questions. We got, let's see, Julian.
Correct this statement if it's wrong, but you go from node and links that you have which are graph structures, to a graph neural network, and allows you to extract what exactly out of the graph structure? Well, depends what you want to predict, right? But
oh yes, so from node and links we extract the adjacency metrics, which is the graph representation, and then this is the input to the graph neural network.
Right.
The graph neural network, we have tons of applications. So it could be used for classification, prediction. It could be temporal or spatial prediction. So they have so many applications.
Okay. So let's say you train your graph neural network, you get the output you want with that. My question is there a way to apply some kind of transfer learning and reverse the process? You don't have the links and the nodes, and you're trying to get that graph, that spatial information from a trained graph neural network and some measurement data.
I think there are GANs that can be applied also to a graph neural network. Is this related to your question? Again,
open question. I have no clue actually.
So yeah, it has been used GANs to generate. So there is a graph GAN that where you can reverse the process. You can generate graphs basically from pre-trained graphs. So yeah, there is an area of operation that's going now. So you can basically, the ultimate goal, for example, would be to generate new buildings or something like this. You input some data and you generate buildings or building. And actually,
So an application I'm thinking of is you have sensor information from multi-zone buildings, but you don't know how they're located or what's their relationship. So could a graph neural network come back to get those spatial information between those sensors and say, oh, that's the layout of your multi-zone building that I can tell from those sensors?
Yes, this will be a great application. Yeah.
Okay.
Yeah, predicting links, right? I think you mentioned earlier, predicting links is one of the objectives. So if I give you a point list of 1,000 BMS data points, and I give you a month of time series data, and you extract hundreds or thousands of time series data features from each of those 1,000 points, theoretically, you could do link prediction and recreate the hierarchy of a BMS system, possibly. Because the lights turn on in this space at the same time as the thermostat turns on, right? So there might be some time series feature which recognizes that you could predict that link because of that feature.
Yeah, yeah.
Right?
Oh, yes, yes, yes.
Something like that.
Yeah, that's correct.
I have a really philosophical question. So if anybody wants more practical questions first. Okay, I'll go for it. Philosophically, you could represent networks, graphs in a flat way. Like you uploaded a flat file into Neo4j, right? So theoretically, and probably throughout all of history, there's been just regular SQL databases full of rows and columns, right?
Mhm.
What is the big deal with graph databases and graph models? Is it speed? Is speed the main thing? What's your impression?
Yeah, so why did they invent graph database management if there is the normal or the relation database? Yeah, basically because of the efficiency and speed of this. Because of course, throughout our experimentation, we are dealing with the small graphs. It's relatively small graph, but if we expand it to big data, or maybe social networks like Facebook or something, it requires much more efficiency to deal with these types of data.
So theoretically, SD4's graph model represented in a relational database probably wouldn't be a big deal, but all of Singapore as a GIS, that would be much faster if you load that. Okay.
Yes. Yeah. Exactly.
So it's similar to time series databases. Time series databases were developed for speed.
Yes, exactly. Yes, correct.
So you could query and for resampling. So like time series, if I want to query a database with 1 second interval data and I just need daily data, your time series database can do that. That's part of the query.
Yes. Yeah,
So
exactly.
Graph databases, something similar.
Yes.
There's an efficiency in the query process.
Yes, correct.
Okay.
Right.
In both cases, graph database and time series databases, is there at some point just like SQL tables with like an abstraction layer, or is it like fundamentally different on the lowest level?
I've done some research in time series databases. It's fundamentally different.
Okay.
The way, the dimension, like the way in time series databases, in order for me to store 1 Hertz data and give you daily data, that's a fundamentally, because if I had a relational database, I'd have to query all 1,000, or not, sorry, 1,000, just second points, and then I'd have to do an operation.
You load everything in memory and you resample.
But in time series database, it's the way it's the fundamentally different structure of the way it's, Graph databases.
I think it should be the same. It should be different, yes.
Yeah.
Fundamentally different, because even the algorithms that are used to query the data, the database itself must be indexed in a way that serves these algorithms.
Yeah.
Yeah, because
I'm not smart enough to explain exactly how.
No, it's okay. Just you saying it's not like just an abstraction layer on SQL database. That's like enough. We don't need to go further.
Yeah.
I can do the reading myself.
If you look at any old any BMS out there, they use relational database.
Yeah.
Right. I want to look at, and if you ask a BMS vendor, I want to query every data point in this whole building for 1 month, they would be like, that's impossible. You'll never do that. It would take 6 months for the query to run, basically. Not 6 months, but a few hours or something. But with a time series database, 3 seconds, boom, done. Here's your data, right? So this is probably a game changer for people who have really massive graphs. So we're working on this digital twin project that Mario's involved with, Pengyuan, right?
Yeah.
Maybe you want to introduce yourself to the people who don't know you here, because you just joined as well.
Yeah, so my name is Pengyuan Liu, and I recently joined the Urban Analytics Lab working on the Digital Twins project. And I had computer science background for my bachelor and master degree. PhD in the University of Exeter, UK. focusing on the geographic artificial intelligence part. And I also worked a lot with the graph neural network perspective. And also, yeah, and after my PhD, I went for a year in Finland for one of the postdoc project there. And then I come here. So,
Cool.
yeah.
We're really happy you could be here for this workshop.
Thank you.
Thank you.
And I guess, Filippo, also, you have a background in BIM and things like that.
Yes, I will present myself later, but if you want.
Exactly, yeah. If you want to stick around, we're having our Buds Lab meeting at 4 o'clock, where Filippo gives his presentation about his work and his background as well. He has a lot of, he's like our Mahmoud 2.0, I don't want to call you, like our new Mahmoud.
Next gen.
Yeah, because of the similar background-ish, right?
Yes, I'm 20 centimeter less height than Mahmoud, but I will try to do my best.
Yeah, okay. Big shoes to fill, yeah. Okay, Mahmoud, I think we interrupted you probably an hour ago. Maybe you want to continue, or do you have other things to show, or?
No, that's all, but I just wanted to show how can we create, how can we play around with Neo4j. It's very easy to use. For example, if I need to create a graph or something, I just type create, and then I specify the first node. This is the first node, and this is the second node, and this is the relation in this format. And these are the attributes. For example, this is the node label, and if I need to add different attributes, let's say name, it will be in the form of dictionary. So and so on. So I can add as many attributes as I need. And that's all. And then when I do this, it will be created like this. Also, if I need to query any data, I just type match, and then I type the first node name. For example, where n the type equals, let's say, wall. Oh, sorry. So yeah, it will be very easy to use if we use the same.
So you're showing us the Cipher language,
Cipher language
functionality.
Yeah.
Cipher seems to be some sort of
query language.
SQL, JavaScript-y kind of.
Exactly. Yes. Exactly.
Python-y.
And also because we can host the graph online, so we can use also the Cipher language to query online also.
So this is a desktop. This is a desktop client. Is it querying a cloud-based?
No, this is locally hosted.
Local? So you're local. You have a local. You're running Neo4j on your workstation right now. If we run models if we have graph models in the cloud, are we paying for it? What is it? Is it free?
I haven't explored this before, but
okay.
Qgis is free, right?
Qgis is, yeah. It's free.
And the Neo4j.
It's open source, but the platform it's like InfluxDB, right?
So if you run it yourself.
Small development projects, blah, blah, blah. Professional is where you have medium scale. What does medium scale mean to them? Is it like 1 million nodes is medium scale, or? Doesn't matter. If you don't know the answer, you don't have to know. What else? After you query your Neo4j, talk about that process a bit. I know you said that you export it as a network X format, and then you have that's build to vec. After that,
yes.
That's your build to vec. Exactly. And you have a repository called build to vec.
Oh, yes.
Can you go to that repository? That is the key repository that I've tried to dive into several times, but I give up very quickly because I don't have enough.
So yeah, this is the build to vec. It's open, and it's based on node to vec basically.
Which is based on Network X.
Node2Vec is graph embedding.
And
But all of them are using, I mean, Network X is a graph library that.
so Network X and Node2Vec is like NumPy and Pandas, right?
Yes, exactly.
Node2Vec is built on Network X, sort of.
Yes.
Okay.
So yeah.
Got it. Okay. So in this repository, you have, this is where you do a lot, that's where you do the graph neural network modeling and prediction, and that's where you integrate the time series data portions, like your temperature, the instantaneous temperature of that particular point is integrated into this process,
Yes.
right?
Yes, yeah.
And you have scripts, so you have built-to-vec repository, but you also have a repository for the paper about thermal comfort prediction. Is Zoom recording that? Can you guys hear me on Zoom? Is this being recorded?
Yes.
Can they hear us? Oh, there we go. I can see it, but they can't see us. I guess that's okay. Do you have multiple repositories or just one?
No, this is just one.
Okay.
I haven't yet uploaded the QGIS thing. I'll upload them.
But that's all. That's the value chain that I was asking you before about. But I'm talking about the paper you wrote about thermal comfort prediction. That's a specific use of build-to-vec, but it's not build-to-vec itself, right?
Yes.
And you have a repository about that particular paper.
Yes.
Right? So there's 2 repositories at least.
Yes.
Okay. Can you give us a small tour? I mean, we've got a few minutes left. Very small tour of those 2 repositories so that we can understand a little bit about what's inside. Yeah, let's start with this one. Yeah.
Yeah. So this is the build-to-vec paper that's used for prediction of thermal comfort. Yeah, basically these are the cell centers that I've used, and I inputted it to Neo4j, and then I inputted them into the build-to-vec, and the result is the similarity between each node and all the nodes in the building and the floor. Okay, so this is the output from. So you get, once you input this data, the output will be each node has its own vector, and once you calculate the distance between these vectors, you get how similar each vector to each other, or each node to each other. So, for example, each node here is similar to different nodes in the floor plan.
So can you step us through your code folder? Like what are these? What do you got in there? You got, it's just a IPython notebook, okay, or Jupyter notebook. Oh, okay. So it's all self-explanatory.
Yeah, so these are the data, the inputs from Neo4j.
All spatial data, that's an export from Neo4j. Okay, got it.
Yes, and these are the cells, and these are the labels of each cell.
Cool.
Okay, and then so these are the data from the users, the heart rate and the skin temperature and the thermal vote, and these are the cells. Then I concatenated all these data together, and this is the feature vector that I got at the end. So now we have the cell, and we have the relevant data and thermal comfort vote, and these are the inputs to the. I input this into the machine learning prediction. I used the random forest classifier to classify the machine learning, and then I reported the results.
Cool. Okay. All right, we have maybe time for one more question. Yeah.
Can I ask, the build-to-vec embedding model is created based on the Node2Vec?
Yes. Yes.
Oh, so well, I thought it's developed based on the graph search, because I probably incorrectly remember from your Viva. But anyway, okay, thanks.
So basically, the build to vec I created as it will include the different models, because I started off with node to vec, then I'll add graph sage and also something else for the temporal data. For example, star. Yeah, I'll add it later. So I mean, it's like a platform for adding different models on top of it.
Ah, okay, yeah.
Can you make like a mind map kind of thing of how all this fits together?
Okay. Yeah.
Or whatever, just some sort of something that kind of gives somebody a way to reverse, know how to connect the dots between the different parts of what you've done. I don't think that it's necessarily necessary for us to replicate what you've done, but it's good to kind of get as an inspiration, for somebody who wants to pick up and learn from it. And we will probably still bug you, even though we don't pay you salary anymore. We'll probably still bug you.
I'd be glad if there is anything
Awesome.
Oh, I thought it's open, but it's still private. I'll open it. So
I mean, I don't know if it's been announced. I guess I don't know if everybody knows this, but tomorrow is Mahmoud's last day at NUS. And next Monday, he starts his new job. You want to talk about that?
Yes, so I'm going to move to a company called Salt Mine. And basically this company is, it's for workspace, workspace recommendation and workspace management, and also workspace design. So the new stuff, they have a platform for the design and recommendation of workspace for companies. One of the affiliates of the company, he has been working with us. One of the affiliates of Buds Lab is Tapish. He has been working with us here, and now he is in this company also. So yeah, so the company contains many people from.
Tapish was the first member of the team. He joined us in September of 2017, and he left us in July of 2019, I think. Yeah, pre-pandemic. He's one of our pre-pandemic.
Yes, Tapish.
Some of you remember Tapish.
So he's now working as a product manager at Salt Mine.
Excellent. Well, thank you very much, Mahmoud. Let's give Mahmoud a party congratulations and round of applause. So we'll take another 5-10 minute break, 5-minute break, and then we'll start the Buds Lab meeting at 5 or 4 o'clock. So everybody's welcome to stay, and if you want, if those of you that are visitors, but
Yeah, sure.